do you prove that you make what you think you made? This video is the first in a series of videos on spectroscopy. I'll put a link to that playlist down below. But what even is spectroscopy? This video is going to give you a broad overview about the field of spectroscopy, and later videos will drill down into the various specific techniques. As a way of introducing what spectroscopy is, let me back up a little bit. Throughout this course, and in the remainder of the course to come, we are going to learn a lot of chemical reactions. They are very nice chemical reactions. Some of them even have really nice names like hydroboration or SN2. We told you that these reactions made these products, but we never proved to you that these are the products that form. How do you prove that you make what you think you made when you're a chemist doing a reaction? Now, you might have done some of this in lab. Perhaps you've gotten a melting point in lab. If the melting point of the thing you made matched the melting point of the thing you were supposed to make, well, that's very suggestive that what you made is what you thought you were supposed to make. But there's a bit of a problem with that. Several molecules can have the same melting point. So just getting a melting point is suggestive that you have what you think you want, but it doesn't necessarily prove that you have what you think you want. We need spectroscopy, spectroscopic tools, to help us prove the identity of the molecule we're trying to make. It's not good enough to just hold up a vial and say, look, I totally made this thing. You can totally believe me. Spectroscopy will help us figure out what is the molecular mass of this molecule, what kind of functional groups do they have, and how are the carbons connected in the molecule, proving the identity of that molecule. So how do we talk about spectroscopy? Spectroscopy uses energy to ask molecules questions. And if that sounds really vague, it is. This is just a broad overview. Other videos will explain each technique in more detail. But spectroscopy uses energy to ask molecules questions. Molecules interact with that energy very characteristically. We detect that interaction, and how those molecules interact with energy gives us information about the answer to the question that we ask. I'll talk more about this in a minute, but it is important at this point to say that certain spectroscopic techniques only ask certain questions. So we have to be very careful that when we're reading a spectra, we're only reading it through the lens of the question that spectrum is asking. We can't expect a spectrum to give us more information than it's able to give. It's only able to give us certain information about certain questions. We need a variety of spectroscopic tools to ask a couple of different questions to really get enough evidence to say that we have in fact made what we think we made. So what are some of these spectroscopic tools, and what questions do they ask of molecules, and what answers do they give us? If we have just a generic molecule, it really doesn't matter what molecule this is. Here are some of the questions that we might want to ask. We might want to look at the molecule as a whole and ask some questions of the whole molecule. So we might want to use mass spectrometry to ask, what kind of molecule are you? What is your molecular mass? Do you have any atoms like bromine or chlorine or nitrogen? We're asking questions about the entire molecule. Within this molecule, there are certainly some functional groups, so we might want to know some things about that. For that, we would use the tool infrared spectroscopy to ask the question, what kind of functional groups do you have? Do you have an alcohol in the molecule? Do you have a carbonyl in the molecule? It won't tell us where or what functional group is next door, but we can get a list of the functional groups that are and are not in that molecule. Finally, this molecule is certainly going to have some kinds of carbons and hydrogens in it, so we might want to ask those atoms some questions. What kind of atoms do you have? For this, we would use nuclear magnetic resonance spectroscopy. There are two kinds of NMR, proton NMR and carbon NMR, and by far, proton NMR is the most important spectroscopic tool we're going to learn in this sequence. Not only will NMR ask what kinds of atoms do you have, but it will also ask how are those atoms connected to each other. And that's really important information. It's really the only way we can stitch the entire molecule together is with this connectivity information that NMR gives us. And notice what we've done here. We've started asking very broad questions of the entire molecule using mass spec. That gives us a good overview of the molecule. Then we drilled in a little bit more by looking at the various functional groups with infrared spectroscopy. That told us some more information, but not anything about connectivity. And finally, we drilled down very specifically with NMR to figure out what atoms we have and how they are connected to each other. These are kind of a hierarchy of spectroscopic tools that can help you drill down more and more into the molecule to build an entire picture of what molecule you are looking at. There are two main reasons why a chemist uses spectroscopy. One is what we kind of talked about. After I do a reaction, I need to prove that I made what I think I made, and I use spectroscopy to prove the structure of the molecule. You may or may not use some combination of these techniques in your lab course to prove the identity of the products of your reaction. The other reason a chemist might use spectroscopy is if we just have a vial and we just really don't know what's in it. If we have no idea what this molecule is, we can use these spectroscopic tools to help us figure out what molecule it is, what its molecular mass is, what kind of functional groups it has, and how they are connected to each other, so we can figure out the structural identity of an unknown molecule. That's probably how you're going to use it more likely in your lecture course, although we rarely actually do that in real life. So again, broadly, spectroscopy works by adding energy to molecules. Molecules will then absorb some of that energy, and they will respond characteristically. And the responding characteristically part is really important. It's much more important than you might think. What do I mean by respond characteristically? If I'm looking at an infrared spectrum and I know my molecule has alcohol, when I run my molecule through the infrared, I should see a peak that corresponds to that alcohol. And that peak should be in the same place every time I run that molecule. Furthermore, if I have another molecule that has an alcohol, but I don't know what the structure is, when I run that molecule through the IR, I should expect to see a similar peak in a similar place corresponding to that alcohol. As I look at various different molecules, all the ones that have alcohols should have this very characteristic peak in common. So let's take a quick look at the three main spectroscopic tools that we learn in this course. I'm not including UV-Vis on this spectrum list because it's really not that characteristic. For each spectroscopic tool, we want to know how it absorbs the energy. What does it absorb the energy from? How does the molecule respond? What do we measure when we run this type of instrument, and what this instrument looks at? So for mass spectrometry, the molecule absorbs energy from electricity, from an electron beam, most of the time. There are certainly other ways to do mass spec. I'm just going to talk about the main characteristic, prototypical version of mass spec, but certainly there are others. When the molecule absorbs that energy from the electron beam, from electricity, the molecule responds by creating cations and breaking certain bonds in the molecule. And that's very characteristic and very important. What do we measure? We measure the resultant molecular mass of those cations. That's important. We'll talk about it more in the video on mass spec, but we measure the molecular mass of the cations that are formed when the molecule absorbs electricity. And as we saw before, this instrument looks at entire molecules. Mass spec looks at an entire molecule. It analyzes an entire molecule, not parts of a molecule, not functional groups, not specific atoms. It analyzes an entire molecule. That may seem like a picky differentiation, but remember, we can't ask more of these tools than they can answer. We can't use mass spec to answer questions that it's not equipped to ask. Mass spec looks at an entire molecule. Infrared spectroscopy, on the other hand, absorbs energy from, well, infrared radiation, infrared light, infrared photons. The molecule responds by absorbing some of those infrared photons and causing certain bonds to bend and stretch and vibrate. What do we measure? We measure which IR frequencies are absorbed by the molecule and which ones are not. This instrument looks at bonds. It looks at bonds. It doesn't look at entire functional groups. It doesn't look at atoms, and it doesn't look at the whole molecule. It looks at bonds. Which bonds are bending and stretching and vibrating in the molecule when they absorb infrared light? And finally, for NMR, the molecule absorbs energy from radio waves. The molecule responds by flipping this nuclear spin of certain elements and then releasing radio wave in response. What does that mean, flipping the nuclear spin of certain elements? And don't worry about that right now. We'll talk more about that in the NMR videos. What do we measure? We measure which radio wave frequencies are released by the molecule, and we can use that to look at individual atoms. NMR looks at individual atoms. IR looks at functional groups, and mass spec looks at entire molecules. So this is a broad overview of the three main spectroscopic techniques. Spectroscopy works by adding energy to molecules. Molecules absorb some of that energy, and we measure the response. And that response, it tells us the answer to the question that we're trying to ask. Mass spec asks questions of entire molecules, infrared asks questions of bonds, and NMR asks questions of individual atoms. By learning how to interpret those answers, we can use all three of these spectroscopic tools to paint a very detailed and specific picture of the molecule in question, proving the identity of that structure.
Thanks for watching. If you like what you saw today, maybe let your instructor know about these videos, or your friends at other schools. Check out some of these other videos and playlists, see what you like. As always, don't forget to like and subscribe.